In this set of videos, we're going to talk about the inverse trig functions. So before we do that, let's just do a little bit of review about inverse functions. I do have some notes already written, so if you need to pause the video and write them down, feel free to do that. Now, inverse functions are something you should already be familiar with. So they're not taught in this class, so it's just a quick review. But if you need to see more about it, you can go ahead and look into some previous videos or in previous sections of the text or online for a more thorough review. So in general, if a function is graphed and it passes what's called the horizontal line test, it does have an inverse. So what that means is that there would be no horizontal line that crosses the graph of a function more than once. Another thing about inverse functions is that inverse really just means like an opposite in mathematics. There's different types of inverses. So with functions, what happens is the points swap. So if AB is a point in F, then BA is a point on the inverse of the function. So it's kind of nice because if you know one function, then you can find the inverse points very easy. You just swap all the values. And the third thing to note, and we're not going to use this as much today, but it is helpful, is that functions and their inverses cancel each other out, and they do this through composition. So remember, this notation is composition when we plug one function into another. So they do cancel each other out, and this tends to be more helpful when solving equations. So I'm just going to make a note of this last piece now. We're not going to use it so much in this set of videos, but it is a helpful thing to remember as well about inverses. So one thing you may note, and I just have the sine function quickly drawn in here. And I have some key points of that sine function rewritten again for us, is that you may notice that this function alone does not pass the horizontal line test. If I were to draw a horizontal line right through it, let's say, right along here, then obviously that horizontal line hits the graph many, many times, right? Because the graph continues forever, it's actually going to hit it infinitely many times. So as the sine function initially stands, it does not have an inverse. But what we can do is we often restrict the domain of a function. So we don't use the whole graph, we use just part of it where it would pass the horizontal line test. Now, because it's periodic, you can do this in many different places. I'm going to be consistent with our textbook here. And what they recommend doing is we're going to restrict it from here at x is negative pi over 2 to positive, pi over 2. So we're only going to consider this part of the sine function right here. Now it's still going to run through all the possible y values, right? And you want to keep in mind too that because the sine function is periodic, you don't have to just cut it here. I could cut it anywhere along the graph that I want to, really, as long as that part of the graph passes the horizontal line test, you can find an inverse for that part of the graph. So what we're doing here really can be extended to any region that we want to, where we want to cut this graph, but this just has to be the most common. So if you look at just this little area, you can see that, well, within this little area, it only crosses that line once. So this right here would have an inverse function. So that's what we're going to do. We're going to restrict the sine function in this case from negative pi over 2 to positive pi over 2. And then we can find an inverse. And that's what you see here. So I only put those key values in from negative pi over 2 to positive pi over 2. And again, this is just one way to cut the graph. So you can extend this idea to other parts of the graph if you wanted to, just focusing on other areas instead. The notation we use for inverses is that -1. So we're still going to use that same notation, but we'll write it as SIN with the -1. And again, remember that the values are flip-flopping here. So sine y equals x means that y equals the inverse of sine at x. And I'll show you some examples, and you'll see it's actually quite easy to understand this concept if we have some examples to go with it. So I'll show you that in just one moment here. One thing I want to point out, though, that's to make this really clear, is that this is not the same as 1 over sine or sine x. This is not cosecant. So these are two totally different ideas. Your inverse function is not your reciprocal function. So you want to be careful, make sure you don't mix that up when you're finding answers, and also on your calculator. So your calculator should have an inverse sine function as well on it. Again, and that's not the reciprocal. They're two totally different things. Now I'm going to use this table just to help me. So again, these are common values that hopefully you already know, but if you don't have them memorized yet, it's okay. Just keep a running list with you. So make a little note card of sine values, make a little note card of cosine values, tangent values, etc. And then that way you just always have it with you. So you're not constantly flipping back and forth or trying to find these values every single time. So I'm going to use this table here to answer the next few questions. Actually, I think I'll just try to put the problems at the bottom so that we can keep it on the same screen. All right, so the first one I'm going to do is we're going to find the exact value of the inverse sine of root 2 over 2. Now, again, you should have this function on your calculator, right? So on my calculator app here, I see it right here in yellow. And if I check my mode, I want to make sure I'm in radian mode on my calculator right now because I'm using that square root of 2 over 2. And yes, you could use your calculator here. To get an answer, right? We could go ahead and do that, but it's giving us a decimal answer. It doesn't give us the exact answer. So that's where it's helpful to know the true values here of the table. But just wants an approximate answer. Your calculator can do this for you. It's very quick. But when you want an exact answer, they really mean in the fraction form with the pi, with the roots, all of that sort of stuff. So I'm going to go to my table instead. Now, remember that if you have something for sine, we can just reverse the order for the inverse. So I'm plugging in root 2 over 2 here, and it's positive. So if I look through my chart and I find root 2 over 2, I see, well, that would have been associated with the angle pi over 4. So that is my answer here. That's it. And again, remember, our inverse function is only defined within these values here. So your x value is -1 to 1, and then your y value, so that would be the output for the inverse function, is negative pi over 2 to positive pi over 2, and pi over 4 is between there. So the list that I gave you is restricted already on those values, so the output that you're getting is in the correct range, right? We're not on like a different part of the graph. So that's it. You just have to reverse the order. Instead of it being xy, it's yx, and you can still use the same table. Let me do one more. And same question here. Again, sometimes I like to put parentheses. It just helps me to clarify that I'm plugging that value in. That's my input. Again, your inverse function is defined for y values between negative pi over 2 and positive pi over 2. So this is the chart that we're using. I am inputting -1/2. So because it's the inverse, that would actually be the y value. And if I look, I see -1/2 right here. And that's associated with negative pi over 6. So my answer is just negative pi over 6. So that's it. We can use our table very, very quickly to find our inverse values. And again, your calculator is nice for approximate values, but you can see, you know, we're getting the same answer, right? 0.7853, etc. is pi over 4, but they're not giving us in the right form. So if it does say exact answer, you don't want to use your calculator. You want to use the fractions, the pi's, the roots, all that stuff, and go to the table. If they want an approximate answer, then you can just use your calculator and get that very quickly. Now we can do similar things with the other trig functions. So let's look at cosine next. I don't know why I drew my graph that big this time, but you guys get the idea. And see, we'll go to, this will be 1. And I'm just doing a rough graph just so we can kind of talk about it. Not the best drawing, but you guys get it. So here's my cosine function. And we're crossing here at pi over 2. This is at pi, 3 pi over 2, etc. And again, if you notice, first of all, looking at the cosine function, you're saying, but it doesn't pass the horizontal line test. It can't have an inverse. So what we do is we restrict the domain. And this is a very common thing to do with functions that don't pass the horizontal line test. We do often do this, not just with trig functions, but we restrict the domain. It's just a matter of where we choose to restrict it. So for this one, we're going to restrict it specifically between 0 and pi. So you're looking only at, in this case for cosine, your x values between 0 and pi. So a little bit different than the restriction we did for sine. And then on this area, again, you're just focusing on this piece here. So this piece would pass the horizontal line test if I were to do it. So again, we're restricting our domain. Now, because I'm restricting my domain from 0 to pi, again, I'm going to make a table of values that we already know, but I'm going to focus just on 0 to pi because that's going to be our restriction here. So I'm going to have 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and then we'll end at pi. Now, hopefully for all your notes, you don't have to make this table every single time, right? So again, make it once or just kind of keep a note card for each function and make a big running list of all the common ones that we're used to. And then that way you're not constantly rewriting the table or finding the values all over again. So when x is 0, cosine is 1. At pi over 6, it's root 3 over 2. At pi over 4, it's root 2 over 2. At pi over 3, it's 1/2. At pi over 2, it's 0. And then we go to negative 1/2, negative root 2 over 2, negative root 3 over 2, and negative 1. Now, these are the main values that we're going to use because, again, we're restricting that domain. I don't need to expand any further. And we're going to do the same thing with our inverse function. So for our inverse cosine, you're going to see that same notation, that cosine with a -1. And again, just please remember this is not the same as 1 over cosine or 1 over cosine x. Totally different things here. So this is our inverse function. And we have the same sort of idea. So y equals the inverse cosine of x really uses the same values as cosine y equals x. And here our y values are going between 0 and pi. And our x values are still going between -1 and 1, right? Because that's the height and the minimum of our graph. So similar question here, we're going to find the exact value of the inverse cosine of negative root 3 over 2. And remember with inverses, if I know what happens with the function, all I need to do for the inverses is switch the order. So for the function, it's xy, but for the inverse, we would switch that order, yx, right? So this is really your input, and then that would be your output. It just changes. So what we would have here, I'm looking for that negative root 3 over 2, which I do find right here. I see that it's associated with the angle 5 pi over 6, and that's my answer. And let's do tangent on this video as well, and we can do the other ones on another video. So we're not getting too long. Do the main ones here. I'll do it in blue. So remember with the tangent function, this is the one with all the asymptotes in it. So you kind of have this repeating shape like this. And again, I'm just freehanding, so you could always use Desmos to graph this a little clearer here. But you sort of have this repeating function that looks like this, and you have these vertical asymptotes that are really sort of blocking that function. And what happens is, I guess we'll do it in orange. And I'm just doing a freehand, so this should be nice and straight. But what's happening here is this one first occurs at pi over 2, and this one's at negative pi over 2, and then it occurs at 3 pi over 2, and so on. So that keeps repeating. And just like with our other functions, you'll see that, as an entire function, it doesn't have an inverse, right? It fails that horizontal line test. So we're going to go ahead and restrict the graph, and we are going to restrict it very similar to sine function, from negative pi over 2 to pi over 2. So we're really just focusing on this piece right here. So just be careful with your restrictions. Both sine and tangent the original functions are restricted between negative pi over 2 and pi over 2, but cosine, we typically use 0 to pi instead, which we just saw. So again, you just want to be a little bit careful because you have slightly different restrictions there. And actually, I made a little mistake here. These should be strict less than sign. Sorry about that, because the graph doesn't actually touch negative pi over 2 or positive pi over 2, right? So again, because you have those asymptotes here, we're not actually touching those values. So technically, we're strictly less than pi over 2 and strictly greater than negative pi over 2. Now, your tangent function is actually undefined at negative pi over 2 and positive pi over 2. It's undefined there, right? Because it kind of goes off to infinity. So even though I'm going up to these values, I can't include my endpoints. So in my table, I'm going to start at negative pi over 3 instead. Okay. And then at the first one, our answer is negative root 3, negative 1, negative root 3 over 3. At 0, we have 0, positive root 3 over 3, positive 1, and positive root 3. So again, those are going to be my key values here when dealing with the inverse tangent function, because we have that restriction. So for inverse tangent, we use tan -1. And again, just to really drive this home, it's not the same thing as the reciprocal function. So please don't mix those up. It's a really common mistake. Everybody does it. So you just want to be careful there. Okay, so here's our inverse function. And again, we're defined between negative pi over 2 and pi over 2, strictly less than symbols there because we cannot include the endpoints because it would be undefined, right? It kind of goes off to infinity. Here for your x values are actually infinite, because if you look along, the original y, again, you're traveling through infinities there. So your output is not restricted to -1 to 1, like the original sine and cosine functions. Your tangent function, the output is -infinity to infinity. So that's why you see that change. And again, we're not going to use our calculator because it does say the exact value here, even though you should have that function on there. And the big thing is to keep in mind that everything reverses. So the input and output for the original tangent function, the values stay the same. It's just that for the inverse function, they reverse. So your input now becomes these values and your output now becomes the angles. So I'm looking for square root of 3, which is right here. The angle was pi over 3, and we are done. That's it. Pi over 3. And remember, we've restricted our output for the inverse function to -pi/2 to pi/2. Pi/3 is definitely in between there, so we don't have to worry about anything. Like I said, there are cases where you may want a value that's further down the axis, and we can find those in other ways as well. But for your straightforward kind of inverse function, we are restricted here between -pi/2 and +pi/2.